So I have my model, now I'm ready to do my Friday balance analysis. I'm going to come over here. Everybody still see this on the screen? All right. So I'm going to come over here. I'm going to go ahead and do my start. I'm going to do my advanced simulation. It's going to come up here, right click. I'm going to do FEM and simulation. Comes up with the first menu we don't have to do. I'm still doing structural. I'm going to go ahead and click OK. And wait like 30 minutes. All right, so when it comes up here, this is the solution type that we've been doing. So solution 101, this is an NX thing. I mean, not an NX. This is a Nastran. This SOL 101 is something that Nastran uses. So I'm going to click on that. And now I have, I can do subcase constraints, super elements, real eigenvalues, flexible body, response simulation, blah, 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 blah. So these are all the different things I can do. The one that we are going to do is our response simulation. So remember I told you like the first step of response simulation is to do find the mode shapes and natural frequencies. Once I find the mode shapes and natural frequencies, then I can come into my model and I can give it a force as a function of time and figure out how my structure is vibrating with respect to time. We will do this too right after this. This is the next thing we're going to do. But there's like a lot of steps. Response simulation it's a lot to do because now we're going from just something sitting there and it's giving us some solution to some set of equations, right? A fixed set of equations. It's usually the homogeneous solution, right? That's easy to find. But once we go from a homogeneous solution to the exact solution, it's a little bit more difficult to do. So there's a lot of stuff we have to do. And there's a lot of stuff to comprehend because when we do something as a function of time, I can take snapshots. This is what my displacement is going to look like at time t equal to 5 seconds, right? When we come and apply a force to something and it bends right, and we find the solution in our finite elements, it's just one solution, right? That's what it is. When we go to response simulation, it's like, well, what time do you want? We can sit there and we can watch this thing vibrating as a function of time. Can you imagine how much space that takes up? It's basically solving the static case for every time interval we want. And we can do that inside NX. We can do all of that. Okay? We'll go ahead and animate something where it's actually, this is how it's vibrating with respect to time when we give it that force. Okay? So that'll be the next step we do. So a lot of times we'll just do this. We see eigenvalues and eigenvectors, see it still has the same solution. When we write our system of equations, we actually, when we come into this and we write it, we have mass times acceleration is equal to whatever. This actually turns out to be, the mode shapes and natural frequencies turns out to be an eigenvalue eigenvector problem. If you were to take vibration, one of the first things you learn is when we turn this into acceleration and we discretize it. So now I have a matrix of equations that I want to solve. I have my mass matrix, my stiffness matrix. I solve that system of equations. There's a way to solve it, and it basically ends up being an eigenvector eigenvalue problem. The eigenvalues end up being the natural frequencies, the eigenvectors are my mode shapes. And in vibrations, you would do that by hand. Okay, that's fairly common. So that's why you see it's the same thing, but we just click on this response simulation. It's not going to change anything different. It comes up and gives us all of this. Typically, we don't have to mess with any of this. We'll do the solution control later. So I hit OK. And it creates everything. Now I have my FEM, so I can go ahead and mesh it. So I'm going to do this. It's the same thing. So the only thing different is that instead of doing 101, I selected 103, right? It's the only thing different. But we're told that we're gonna do mode shapes and natural frequencies. So I'm gonna do my mesh collector, I'm gonna do 3D. I'm gonna come over here and I'm gonna go ahead and select my aluminum 6061. There it is, I hit OK. And now it's like if I was actually trying to compare something with a chest, I would go in and specify temperatures and tell it to use this as my initial temperature for all of the nodes in my body. All right, so I've got that. Now I'm going to go ahead and mesh it. So I click here, I'm going to go ahead and do 4. Remesh, I'm going to use that. All right, so there's my mesh. And here we have, I don't know, I can go ahead and see here. All right, so I have 328 nodes times 6 degrees of freedom per node, right? So that's how many mode shapes and natural frequencies I can solve. When we're doing something, remember I said you come over here, we put our accelerometers and we displace it, and we let go, and we get something like this for every accelerometer. So, oops. So if I have 6 accelerometers, I'm going to get 6 of these. I'm going to use those 6 to find the mode shapes and natural frequencies. Of course, since I only have, well, in this case, I only have 1, 2, because this one's fixed, right? So there's no point to put an accelerometer there. So typically I have 1, 2, 3, 4. I have 4 accelerometers on this. So the most I'm going to be able to find is 4 mode shapes. So if I come over here and I put 4, 5, 6, 7, 8. I now have 8 accelerometers on here, so now I'm going to be able to find 8 mode shapes and natural frequencies. As I move along the mode shapes, what happens is when we look at this, most of my energy, if I take this and I fix it and I pull it down like this and I let go, it's basically going to vibrate back and forth like this, right? That's what we see. That's what we see with our eyes. All of our energy is in that first mode. All of the energy that I put into the system goes into that vibration of the first mode. But all the other modes are still there. When I add them, it's like a series. If I have, I don't know the exact series, but let's say sine of x is going to be equal to x minus x squared over 2 factorial plus, I don't know, x cubed over 3 factorial. I'm making this up, minus x to the 4th over 4 factorial. Something like this. This is a series, right? If I want a more exact solution, what do I do? I start adding more terms, right? But these terms are small compared to this term, right? Same thing with mode shapes. All of my energy is in that first mode. So when I take the first mode and I'm using that to describe the displacement, it's actually going to look pretty close. Not right on, but pretty close. I want a better solution, I'm going to add the second mode to it, right? But as I'm adding more modes, these values are smaller. These terms are much, much smaller, right? Same thing with my mode shapes. My mode shape is going to be much, much smaller. So the displacement that my mode shape adds to it is going to be very small. So we start getting to the point where our accelerometers can't measure that displacement. So when I do modal analysis and I can put 100 accelerometers on my thing, I'm like crossing my fingers, okay, that I can get at least 5 modes. If I can get 5 modes, I'm pretty darn happy, okay? But that's a rarity. Okay? I'm going to be able to get 5 modes, okay? 5 natural frequencies. I can say I have a pretty good result for first mode, second mode, third mode. Then it starts getting a little shaky. Okay? because of the accuracy, the sensitivity of the accelerometers. I cannot get beyond that. So when we're actually doing something, it serves no point to go out 10 modes. Okay? Now here we're learning it, so we use 10 modes to just, just for the fun of it kind of thing. But in real life, in real situations, if I'm actually doing my systems identification, I'm only going to have like 4 modes to work with. 5 modes at best. Okay? More likely just 3. Okay? I would accept less than 3. So that's typically what we have to work with because of the accuracy of the accelerometer. So here we usually do 10. I mean, there's no need to go beyond 10. Okay? What we're doing is, remember I told you we're solving an eigenvalue, eigenvector problem? If I have 328, multiply that by 6, that's how many answers. That's how many answers I get from an x. It's solving that system. I can't tell it just do 6, right? I can't tell it just give me 5 solutions. It is actually going to it's going to solve eigenvalue, eigenvector problem. It is going to give me 328 times 6, roughly. 328 times 6 natural frequencies. And the same number of motions. How does it know which one to give me? How does it know which one to give me? Well, there's numerical techniques, there's numerical ways to figure out which one to do. One is to look at, we'll look at it, when we do response simulation, one of it is to look at the mass matrices associated with it, kind of like how much momentum is along a particular direction. So it can do that. So it'll actually, we can look at that and use that to decide how much, or which natural frequency to use, or which ones are our natural frequencies. That's pretty easy to do. But it is actually, when we're solving the problem in NX and in other software packages, it can give us that many mode shapes. We're just going to look at which mode shapes contain the most energy. There's a way to do that. And that's basically what it's doing. When I say just give me 10 modes, it's going to give me 10 modes. It's going to give you the first 10 that it finds based on the mass matrix. All right. What is the other thing? All right. All right, so I have a mesh. I'm going to go ahead and go to my sim, and inside my sim, I'm going to come over here, and I'm going to go ahead and fix one of the ends. So I'm going to go ahead and do fix constraint. All right, so I'm still going with the cantilever beam. All right, so I have my boundary condition. I'm pretty much ready to solve for it. Before I solve for it, I'm going to come over here on my solution. I should be able to come over here and go to the solution parameters. That's not what I want. I should still be able to get to this, but I'm just looking for. All right, remember I said response simulation, we need to find the mode shapes and natural frequencies before we can actually solve for something as a function of time. That's what I was clicking on. So it automatically did everything for me, it didn't let me pick anything. So we need to go ahead and do the eigenvalues, the real eigenvalues. Real eigenvalues, if we're going to be able, it'll let us, we'll see what it will let us do. Response simulation, it wouldn't let us do anything because basically it's going to solve for the mode shapes and natural frequencies in the background. Here, I want it more direct, so I want to be able to look at each one separately kind of thing. So if we were solving the problem, if I gave you something, here's a function of time, how is this thing displacing with respect to time? What is the acceleration at this point? Then we would do response simulation. But here we're just looking at the mode shapes and natural frequencies. So I do need to, I thought it would let me get it the other way, but it's not going to let me pick it. So we want to do real eigenvalues. Now it'll let me go in and pick stuff. Now I should be able to say, okay, and actually, this is what I didn't get before. So once I get okay, in response simulation, it didn't give me this menu you see right here. When I did eigenvalues, or when I did eigenvalues, it shows me this right here. This is basically this Langkos. This is a solution technique to find the mode shapes and natural frequencies. This is a solution technique. This is typically the one that is used. Okay? This is the other method that's used. When you go to other software packages, they'll basically, everybody has the first one. Okay? Everybody has that method. And then you'll see the other ones, you'll have maybe one or two other methods that you can use to find. All it is doing is using that method to find the eigenvalues and eigenvectors. The mode shapes and natural frequencies. All right, so here comes the data. I can click right here. This edit comes up here, and then it's going to down. Typically, we don't do anything, but right here is our frequency range, lower limit, upper limit. When we solve for mode shapes and natural frequencies, I said however many degrees of freedom we have in our system, that's how many mode shapes and natural frequencies you can find, right? So we get a lot of what I call, or what's termed junk modes. That means they're not real physical natural frequencies and mode shapes. Okay? So we call them junk modes. It's part of the solution to the system of equations. It is a solution to the system of equations. Okay? But it's not real. Okay? It's just part of the numerical solution. So it's termed a junk mode. And a lot of times we'll get those mode shapes and natural frequencies, they'll be below 1 hertz. I've already told you, when I have a big structure like a bridge going across, the Rio Grande, it's a big bridge. The substructure is made out of concrete, right? So it has a lot of mass. So its natural frequency is definitely going to be less than 10, but I didn't say below 1. To be below 1 hertz, it has to be something really, really big and really heavy. Okay? Extremely big and heavy to be below 1 hertz. So one technique of getting rid of all these modes so we don't see them is if I tell it to find 10 modes, it's going to give me the first 10 modes it finds, and probably none of them are going to be acceptable. So one way, this is when our structures get more complex. This is very simple structure, right? For the homework, I'm going to post later on, we're going to have a truss structure. This is actually a physical structure that was built. Okay? That was pretty neat. We did a lot of model analysis on it, shook it up and stuff. And in the end, we actually, finite elements, we recreated the whole experiment. We did our systems identification, and this was the structure that we were thinking about taking up in the space shuttle kind of thing. That was really neat. here and find the mode shapes and natural frequencies. Okay? The cantilever beam that's fixed, right? Fixed free boundary conditions. So a lot of stuff is free. How do I find the mode shapes and natural frequencies of a real structure with free boundary conditions? I basically have to levitate it and then shake it, right? And get my acceleration. So one of the things, we hung it on big springs. So we have this big old structure, I don't know, it didn't weigh too much, maybe like 40 pounds, but it was mounted on big old springs. And we could come in and we could hit it with our hammer. We could shake it. We had actually a little shaker. Basically a shaker, it just looks like a paint bucket with a little thing coming out. And you put it what's called a stinger, but basically it's a little tiny rod that's very flexible. And you attach it to something and you vibrate the shaker at whatever frequency you want. Okay? And there's lots of different techniques to actually vibrate the structure. So we would come in and we had shakers in X, Y, and Z. Now, when this thing vibrates, I know exactly what points are not going to move when it vibrates. Okay? Anyway, so I got off track. So when we do our analysis, this is a very simple structure, but when we go to more complex structures like that space ring I'm telling you about, I'm going to have a bunch of natural frequencies. It's not going to know which one to give it. Okay? So like the first 10 or so are going to be jump modes. I'll see it looking and it's going to look nice and pretty and everything, but it's not a real physical mode. Okay? So part of the problem in finding elements when we do frequency analysis, mode shapes and natural frequencies, is deciding, is that a real mode? Is that actually a real mode? Is that my structure going to actually vibrate at that mode? All right, so one thing is I can come in and put 1 hertz as the lower limit. So that means it's only going to give me natural frequencies that are above 1 hertz. So now I can go ahead and hit OK, and now OK right here. And now it's going to kick me in here where I can do my mesh and do my boundary conditions. So I'm going to go ahead and mesh this up real quick. 3D, I'm going to go ahead and pick my material. 60, 61. Okay. Mesh it. Let's mesh. 5. Alright, so there's my mesh. Let me go ahead and do my boundary conditions. There's my boundary condition. So now I have it. Our boundary condition turns up in our solution displays when x is equal to 0, right? When I have a fixed boundary, when I fix the modes in terms of x, y, and z and rotation, I'm physically, that's part of my model, right? When I come in and add a force, the summation of force is equal to mass times acceleration, right? That force shows up in the acceleration term. It does not, so if I put a force in here, it's just going to ignore it. I'm finding the mode shapes and natural frequencies. If I put a force on this, it is just going to ignore it. It doesn't do anything. When I do response simulation, that's where my force comes in. Now I can solve my model as a function of time. That force has nothing to do with the mode shapes and natural frequencies. That has to do with how it's going to vibrate, okay? How it's actually going to be moving when I apply that force. So mode shapes and natural frequencies, it's like a characteristic of that structure, okay? It's a characteristic of that structure. Every structure is going to have a unique set of mode shapes and natural frequencies. All right, so I've got it. Basically, I'm done. I'm ready to solve the problem. So now I can come up here and I can hit solve. Solve. Huh? What did I just say? Did I not explain that already? No, I'm serious. So the force has nothing to do with the F. The force comes in with F equal ma. So when I want to find how my structure is conforming as a function of time, in other words, I come in and I want to know what is the displacement at that point at 5 seconds, then I would have my force in there. The mode shapes and natural frequencies, finding the mode shapes and natural frequencies is the first step to being able to do response simulation, i.e. where we have a force on our structure. So our mode shapes and natural frequencies are a characteristic of our structure. We do not need the force to find mode shapes and natural frequencies. That has nothing to do with that. So all we're doing here is finding the mode shapes and natural frequencies. Doing response simulation is a much more difficult problem. All right, so it solved it. I get results. And look what it shows me here. Here's my 10 modes. I told it to find 10 modes, right? I could have told it to find 5, and it should only give me 5. If I look here, this is my first mode. My first mode, what did I guess? I said like about 100, right? My first mode is at 182 hertz. What's 182 hertz? Where am I? Not that one, right? What's 182 hertz?
182 cycles per second.
182 cycles. What the hell's a cycle? I mean, what's a cycle? So that means basically this hand is going to go down 182 times in 1 second. Right?
Yep.
That's basically what it is. We see hertz and frequency, how fast something's rotating, right? It's going to make so many revolutions per second kind of thing. All right. So 181 hertz. Then our next mode is at 457 hertz. I'm going to click on my first mode. Typically stress, I'm not going to get much from the stress. And to be honest with you, I have no idea what the stress is in the first mode. Stress will become important when I do time, right? When I start looking at how something is moving with respect to time, then yes, I'll stress, I'll look at the stress. But for now, I have no idea what it is. It makes no sense to me. I'm going to look at my displacement, and my displacement, wow, how long did I make it?
12 inches.
And it's moving,
76.
oh man, what did I do wrong?
Is that about?
Huh?
Never mind.
Nothing? I didn't helium. I did nothing wrong. Nothing. It is a solution technique, right? Finding the mode shapes and natural frequencies. All we're doing is finding the solution to a system of equations. I'm going to go to the second mode. It's moving the same amount. I'm going to go to my third mode. Of course, you can't really see how these are moving, but that's what it's still moving here. It's moving the same for all modes. That's a good thing. All it is, this is just the solution. That's the solution they came up with. I made it a little bit different, and then I have no idea how much it's going to change. It's just the solution. The number, the displacement is meaningless. Typically what everybody does is they normalize it. So if I come over here and I click on this, and I should be able to result smooth, I should be able to normalize this. I click on the results, nodal, scale, absolute. Now, 1, 82. I should be able to normalize it. I think that's going to be just go back. All right, I'll find it. There's a